Okay, so maybe it's time to start again. As usual, we have lots of work to do. So on the upper board, I've put up a number of facts, some of which we've discussed, most of which we've discussed, others of which maybe are fairly immediate. Let's just go over them quickly. So first of all, there's a little diagram consisting of the main maps we're looking at. So nu is like the normalization map from the, well, cotangent bundle to the sphere bundle, maybe the cosphere bundle. Anyway, it doesn't matter. We're just mixing up cotangent and tangents anyway. Rho is the length function on the fibers. This funny round df, that's the Clark differential, and there's this basic important fact that the support of the differential cycle of any Monge-Ampere function, for that matter, in particular any DC function, is always contained inside the graph of that guy. So here's another couple handy facts about the Clark differential. First of all, if I'm at a local extremum, then that is indeed reflected in the Clark differential. So the zero must belong to this Clark differential in those circumstances. Second of all, the Clark differential is sub-additive in the following sense. So it's some convex set valued function, if you will. So, but if I take the two functions, I add them up, and want to compute its Clark differential, that's some convex set at some point x. It's always contained inside the so-called Minkowski sum of the two individual Clark differentials. Minkowski sum being just the set of all sums of elements of the first and of the second summands. Okay, so we defined what an aura was for a WDC set. So basically, it's a non-negative function for which non-negative and well, anyway, it's that. So one other thing. So one other thing about the Clark differential. So maybe. Which will be handy. So for us in this lecture. So if you look at take a vector v and a point x. So I take the dot product, say, of v with that subdifferential. So that's now going to be some set of real numbers. So if you will, so it's I guess some interval in fact. And so if I take the largest and the smallest of those inner products, well, the largest one dominates the upper directional derivative in that direction v. And the infimum is dominated by the lower directional derivative in that direction. Okay, so just some fairly basic stuff. So what else? So next, so just proceeding in order. So I'm also going to define something else. So some other sets that are related to this Clark differential. So the Clark differential again is the graph of that Clark differential is some kind of set theoretic version of the graph of the derivative. So we have this current theoretic version. Likewise, what we're working on is to produce a current theoretic version of the manifold of outward normals, unit normals. That's our n of f, which will eventually be n of a. We also have associated with that a set theoretic version based on the Clark differential. So basically, we just look at the points of the boundary of a, and we just project all the Clark differentials on the boundary of A out to length 1, at least if we can, if they're not 0. Okay? And it's handy also to identify the projections of the ones of length at least epsilon. And in fact, this latter set is closed, and if I take epsilon small enough, then that always contains the support of this current n of f that we defined. Okay, again, that's a consequence of our definition of n of f over here, which we'll discuss in a moment, and of this inclusion for the support of the differential cycle. Okay, so yes. Okay, so so here's what we do. So basically, we look at so the differential of f. So think classically. So I've got a C2 function or something, and so I look at the graph of its derivatives, and then I just normalize all of them, okay? And I'm interested in what happens. I'm trying to construct the normal manifold to a sublevel set, say. So I just look at the ones sitting over the boundary, and I just normalize them, okay? So I'm doing the same thing. I'm just taking the Clark differentials now. And sometimes those might be 0. Well, in fact, a lot of them will be 0 because, in fact, A is a 0 set of f, and and the critical points have this property that the 0 does belong to the 0 section, to the Clark differential. But essentially all I'm doing is just sort of blowing them out. And these things are sort of candidates for set theoretic normals to A. Okay? And I can also be a little bit more restrictive. Thank you. Blowing them out, I just blow out the ones of length of some fixed arbitrary length, say some small arbitrary length. Okay? So in fact, so what about it? So again, so maybe one convenient way to write it, I wrote this normal cycle of F as that boundary. So as we recall, this F is 0 is a weakly regular value, so D of F is somehow supported away from the 0 section at A. So so basically all the sort of legitimate gradients on the outside of A have length at least epsilon, say. And so this last inclusion follows from that. So I just push them out. Okay, at least if epsilon is small enough. Okay, that's going to be important for us. Okay? Are we okay? Maybe you'll mull it over. Yeah.
The difference between N of F and the other one?
These guys, so N of F is a current. Those guys are sets.
Sorry, support and
Yeah, so here's the support of N of F, and these guys are basically gotten by looking at the Clark differentials. These are set theoretic objects, and just normalizing them, just dividing by their length, just looking at the parts that live over the boundary of A. Okay? All right, so yeah, I noticed, actually maybe in some way, I can't quite remember, maybe here's another expression for the normal cycle of F. It's actually kind of better in some ways. So for example, if I add that D of F restricted to pi inverse of A to the D of F restricted to pi inverse of the complement of A, of course, to get together, I've got what? I've got D of F. D of F is a cycle, so the boundary of one is minus the boundary of the other, and so why didn't I just do that? You tell me. I don't know. So that's one other construction. And then finally, there's this third construction, which we get in this fashion, just by taking the differential cycle, just looking at the part of it that lies right over A. And I guess the point is that somehow the part that lies right over A somehow interpolates between these big differentials outside of A and the 0 section, okay? And we just sort of interrupt them as they traverse this path from big values to 0, interrupt them at some value R0, slice there, and then renormalize. Okay? So that turns out to be the same thing, at least if R0 is small enough. Okay? Yeah. So finally, another consequence of this definition is the following. I could also take my differential cycle and slice it by F, essentially look at the graphs of the differentials over other level sets of values larger than 0, okay, and then renormalize. Those are candidates for the normal cycles of slightly larger sublevels, and in fact, it's a formal consequence of the definition that N of F, as defined here, is the limit of those things in a flat sense. Okay. All right. Yeah, so what else? So this last board is maybe not quite so essential for us right now. Maybe I wanted to say one word about why the first two lines here is actually equal to that third line. Okay, so that has to do with this funny little proposition there. So this is funny. So again, we're creating this sort of current theoretic formalism for ordinary differential calculus in a sense, and so all these obvious things are maybe not always so obvious. So on the cotangent bundle of any manifold, say Rn, maybe it should have been Rn, but let's say Rn, there's a canonical symplectic form, but there's also what we call the canonical, maybe sometimes called tautological one form. It's as a primitive of the symplectic form. Its exterior differential is the symplectic form. I call it alpha again, so there it is. So again, it just measures the displacement in the base space in the direction of the cotangent vector that you're at, okay? And well, of course, if you're on the graph of a differential, the cotangent vector that you're at is the differential of the function there, isn't it? Of course it is. And well, in this quadratic setting, it's not completely obvious, but it turns out it really is true. Okay, so here df again is some kind of funny thing. F is in general just Lipschitz, so I guess strictly speaking, this is some kind of Whitney flat cochain or something. So, but this is this makes sense. Okay, so furthermore, I guess it turns out, you know, I mentioned the sort of difficulty with this theory that you know, if I just look at the axioms for the, you know, that come from corollary A of last time for the normal cycle of a set, somehow it's far from clear. In fact, you know, it's unknown whether if I take a diffeomorphic image of that set will satisfy the same properties. Well, in fact, in the case of these WDC sets, we can already see that it works at least on the level of these n of f's. So basically, I can, if I have a anyway, that's not important for us. You can contemplate that at your leisure. This last thing maybe I hope to get to towards the end of the lecture today. Okay, very good. So any questions here? Okay. So here are our goals. So sort of maybe slightly ambitious project for this afternoon's lecture, but let's see what we can do. So first thing I want to do is prove the Gauss-Bonnet theorem for this n of f, and eventually with a view to showing that this n of f doesn't depend on f at all. Okay, we'll show that it satisfies the hypotheses of corollary A. Okay, and the key point will be this thing, and then the one you all been waiting for. We'll at least give some kind of formal proof of the kinematic formulas, and the intent is in the final lecture to make a connection between the formal proof and the actual current theoretic constructions. Okay. All right. So about 1a. So what I want to show. So in this setting, I want to show. So the claim is as follows. If I integrate over this normal cycle, my form kappa 0, which, as you recall, is it's lambda. It's the pullback by lambda of the volume form of the sphere. So this thing here represents, under classical conditions, it represents the integral of the determinant of the second fundamental form. Okay, so the claim is that this is equal to the volume of the sphere times the Euler characteristic of A. All right. All right. So that's the claim. So I want to do this in two steps. So first of all, let's take R. Say take some R, maybe slightly bigger than 0. I guess here that's the way to say it, right?
How are you
Yes.
defining the Euler characteristic?
Oh, yeah. So we'll see that it's well defined, and so in fact, so here's the situation. I'll just go ahead. So here's we'll see the following. If I look at this set here, say a slightly enlarged version, this thing is a Lipschitz domain, so it has a well-defined Euler characteristic, and the 0 set A turns out to be a deformation retract of this guy. Okay. So in fact, maybe that's while we're on the subject, maybe it's worthwhile to consider how that goes. So A is a deformation retract of this guy. That's going to be a key point. So, okay, I don't want to formalize it too much, but here's the point. So here I've got my WDC set A, okay, and out here I've got all these sort of quasi-regular things. And as you recall, all the Clark differentials out here are not 0. So maybe we have these guys, but they never go down to 0. Okay. So now what that means, since, as I should have written up here, the Clark differential is an upper semi-continuous set function, I can find a little smooth vector field. Well, let me also, while I'm at it, define something else. Let's say a vector field, say V, say some Lipschitz vector field. say, defined on, say, one of these actually regular level sets, we'll say it's outward if what? V of x dotted with any w for w in the Clark differential here. If I take the minimum of all these guys, this is positive always. Okay? So this has the virtue, in view of this string of inequalities here. If I flow, say, in the direction v, then I'm definitely going to increase f. If I flow in the direction minus v, I'm definitely going to decrease f. Okay? Furthermore, this condition is a convex condition. If I take some positive linear combination of outward vector fields, it remains outward. Okay? So that means basically, since I can, well, by upper semi-continuity, I can basically find outward, constant outward vectors in the neighborhood of any given point. Okay? Simply take, if I'm given some point, simply take some vector that has this property at that point. By upper semi-continuity, it'll have that property, that same vector will have the same property at nearby points. Okay? And then because it's a convex condition, I can use a partition of unity and build a whole outward vector field. Okay? All right. And in fact, maybe I can even do this since in fact the differentials are bounded away from 0 in magnitude outside of A. I can construct a flow. Okay, so first of all, can build one. We can construct a flow, say phi of t comma x, such that, I guess first of all, how do I want to do it? So if I compose f with phi, take the t derivative here, I guess maybe I'll take the upper, how do I want to do that? Plus, I guess upper bar. Okay, so this guy here is going to be say. Oh, what I want is this. So I want the lower one to be at least some positive epsilon. Okay, and the speed is finite. Okay. So what does that mean? Basically, this flow is going to, first of all, because and bounded below. Okay. So that means I can just flow. As I make this flow, I'm actually flowing toward this set in this as measured by the function f. And furthermore, because the speed is bounded below, these things actually going to converge. They're not going to spiral around. They're eventually going to hit the set. So there's my deformation retraction. I hope that's at least a little bit convincing. Okay? So that's the key step here. Alrighty. So in view of that, I claim I want to show the following. So that means, so the Euler characteristic of this set here is the Euler characteristic of A for small r. So if I replace this by this, there's no change. Now I want to replace this by what? By that. Okay? Replace that by that. So let me just give this a name. I'll call that n sub r just to be definite. So the next claim is that if I integrate over n sub r kappa 0, I'm going to get, again, volume of Sn minus 1 times the Euler characteristic of now this guy, which as before is Euler characteristic of A. Okay. And then I guess if I can do that, I'm done. Well, why? Because of that limiting condition. This takes discrete values, if you will. Okay. Okay. So why is this? So here's a subclaim. Or what I'll call it proposition. So it's like some kind of like Lipschitz-Poincare-Hopf type deal. So suppose I've got some smooth, or not smooth, but say some compact Lipschitz domain. So maybe locally, maybe it's so it's given, say, it's a sublevel set of some Lipschitz function. And suppose I've got a vector field which is outward of x in the same sense. So maybe I can measure it with respect to the Clark differential of this Lipschitz function. And so the Clark derivative, this idea of outwardness, the whole idea of Clark derivative is a very general notion. It depends on Lipschitz stuff and not on DC stuff. Okay? So under these conditions, basically I want to say that the degree of V, the degree of V restricted to the boundary of X, which is now some Lipschitz hypersurface, is actually equal to the Euler characteristic of X. Okay? So I don't want to belabor this thing, but so the point is I've got this thing which is roughly outward, and well, okay, I'm just going to wave my hand through this thing. So again, the idea is that if I smooth this thing about a little bit, well, again, because of the Clark derivative behaves so well by upper semi-continuity, basically, this vector field is still outward of the smooth thing. The smooth thing has the same Euler characteristic, and now I just apply ordinary Poincare-Hopf. No biggie. Okay? Alrighty, so that's good. So another way of saying this is that if I look at, well, I guess what? Let's just fancify this thing again. So I look at yes. Yeah. Okay. So again, so it's just by smoothing, say. So we know. Yeah. Is that enough?
I was right.
Okay. Very good. Yeah. So so what's the point? Maybe if I look at let's look at the following current. Okay. So maybe even this one. Totally fancified thing. I look at the boundary of X here. Okay. So now I've got some n-1 dimensional current up in the sphere bundle, and I evaluate this at kappa 0, then I'm supposed to get, well, I guess the volume of Sn-1 times the Euler characteristic of X. That's the same statement given in fancy terms. Okay? Okay, so now what can we do? So now if I've got one of these slightly enlarged domains, so now let's take X to be equal to one of these guys, okay? And now I've got this thing n sub r, this current that lives over the boundary of X, okay? And let me take some outward field V, outward unit field, say. And well, okay, so support of n sub r is contained inside the graph of or say nu of the graph of the differential restricted to the boundary of X. Okay, that's just the one consequence of my support condition here. Okay, so now the point is, if that's the case, because V has this special property, so I mean, so what's the deal? So here's my df at X, say, and so here's my V. of x is 0. And so basically this guy has positive inner product with everything like that. So I guess it's possible to define like some nice Lipschitz homotopy that takes this current here basically to the graph of this vector field. Okay, so what's the real point here? You know, these things live inside the sphere bundle. I want to basically, I've got some fixed vector each point. I want to deform everything over to there. I can do that provided the support I'm looking at is never actually antipodal to the given vector. Okay, but this condition, where is it? This condition implies that that is never the case. That is never the case. So to get a current supported on the graph of V restricted to the boundary of X. Okay? Okay, so in other words, and basically, and this thing, it just acts in the fibers and not in the base points. Okay? And now I claim that the end point of this Lipschitz homotopy is precisely this dude. Okay? I guess it's unit, so I don't need that. Why is that? Well, basically because it's supported on that graph, so there's some kind of constancy theorem involved. It's got to be some constant multiple of the fundamental class of that graph. Which constant multiple is it? Well, in the course of the homotopy, nothing, the projection of n sub r by pi star never changed. So it was always the boundary of this enlarged region f less regular r. So that, with multiplicity 1, so indeed this ending point of the homotopy is exactly the graph of f. So in fact it equals id v star boundary x. Okay, and so since everything worked with a homotopy, this was true, and now where are we? This is true. I'm declaring victory here. Okay. All right. So our claim is proven. Okay. So 1A, task 1A is complete. Yes.
This IDV
Mm-hmm.
just number, right?
So I guess, so let's, yeah, so what is this thing? So V is my vector field. So what I'm trying to do is yeah, so I'm just trying to jack the thing up to a current in the sphere bundle. Okay, so this is the current representing the graph of V over the boundary. Okay? All right. Okay, so what about 1B? Okay, so here's where things get interesting. So the key step here is this beautiful observation of Pavlitsa and I don't know Pavlitsa's first name. Do you know? David Pavlitsa and Luděk Zajíček. So so it's the following thing.
Polish and Czech or something?
Probably both Czech, I think, right?
Both Czech.
So I guess the Czech school has this, admirable interest in the subject of DC functions, and so this is one thing that came out. So here's a lemma. Okay. All right. So what does it say? So suppose I've got a couple of convex functions. Okay, and I want to consider I'm going to consider this family of set-valued functions. So this is like some overestimate of the Clark differential of the corresponding DC function, okay, which is a good thing. Okay, so what they want to say, so we can paraphrase it as follows. What they say is that if I look at the graph of this DC function, and let's look at the set of all tangent planes, tangent hyperplanes to this graph. Well, tangent in what sense? Tangent in this sense. If I take these to be the slopes of those hyperplanes, then the set of these tangent hyperplanes is roughly as big as you expect it to be. We're in Rn, so these tangent hyperplanes should be roughly n-dimensional. Okay, so let's see if we can get this right. So let's look at the set of all affine functions from Rn to R. Okay, where lambda of say y is expressible as g minus h of x plus v dot y minus x for some v belonging, let me call it something else. V is special for us, xi. For some xi belonging to d g of x minus d h of x. Okay, so here's some subset of the space of affine functions. Space of affine functions, of course, is some n plus 1 dimensional space, but this guy is sigma finite with respect to Hausdorff n-dimensional measure. Okay, so I don't want to get into the proof of this. It's beyond me right now. Let me just make one remark. It's closely related to this. In fact, it's a consequence of this sort of basic fact from convexity. So there's this paper of Avold, Larman, and Rogers from maybe early 60s, I think, in which they prove the following. This is just a completely cultural remark. Has nothing to do with the main line of our discussion. So it says the following: says if you have a convex body in say n-dimensional space, and let's look at the set of, sometimes in the boundary there will be actual line segments, these sort of flat parts of that thing. So let's look at those line segments, but let's just look at the directions of the line segments. We just take the difference of the endpoints and normalize. Well, let me see if I can get this right. So I think then that the set of directions of those line segments is, so it's some subset of the n-1 sphere. If I'm not mistaken, it's n-2 Hausdorff sigma finite. Okay, so this is like the key. This is related to the key step there. Okay. All right. So what does this? What does this tell us? So. Yeah, that's it. So let me just leave it at that. So yeah. So yeah, here's a corollary. Let's look at the set nor epsilon of F. So we're back in our original situation. F is my aura. It's a DC aura. It's 0 is weakly regular value. I've constructed the set nor epsilon, okay, that contains the support of the normal cycle. So this guy here is some closed subset of the sphere bundle. I claim that this guy here is H n-1 sigma finite. Yeah, so it's defined here. Pay attention. Sorry. Yeah. Yeah, okay? Yeah. Yeah, so Yeah, so how's this work? Let me just draw a picture. So again, we had this little picture here before, where A was just this little line segment. Okay. And now we look at the aura for this thing. Okay. And now the Pavlich-Zajíček lemma says that, well, if we look, excuse me, I've made a big mistake here. I mean, this is actually true, but we can't get it yet. So,
The maximal dimension this thing could have?
well, it's the expected dimension. If everything is smooth, it's the expected dimension.
All the affine
Planes, it's like affine functions like n plus 1 dimensional, right?
plus 1.
Yeah. So it's Hausdorff codimension 1. Yeah. So here's what I want to say. So I want to say that the tangent planes to A, this set here, is n minus 1, is h n minus 1 sigma finite. Okay? So what do I mean by this? So these are going to be tangent planes as measured by nor epsilon. So nor epsilon are all these unit vectors attached to points of the boundary of A. So let's just say exactly what this is. So affine planes, in this other picture of affine planes, maybe is Sn minus 1 cross R, the sphere cross R. Let's discuss it in those terms. So these guys are going to be the set of all v comma t in the sphere cross R, where I'm sorry, let me do it this way. So v comma v dot x in Sn minus 1 cross R, where x v belongs to this set. Okay? So in other words, these are, so this is a direction, this is a number. So basically I take a direction, this like represents a class of planes, and I just hoist it up to level to where it just touches at x. All right? So again, if everything is smooth, then these are precisely the tangent hyperplanes to A. Okay? So notice, incidentally, that somehow we've not differentiated, somehow we've reduced this. This is not all of nor epsilon of f. We've definitely lost information in a sense. Okay? Maybe the claim is, given the step 2 in the proof of theorem A, as you may recall, we might expect that well, this thing is no larger than nor epsilon because of the absence of double points, but actually this is just a set, and it's like we've lost control of it somehow. I don't know any reasonable sense in which this thing is Legendrian, say. I don't know that it's rectifiable in any sense, but nonetheless this is true. Okay? Okay, so why is this right? So in this picture, what are these planes? Well, I guess it's sort of, this picture is sort of limited in, I guess, so the hyperplanes now, I guess, are these points. All right. But they correspond to actual tangent planes to the graph of the function. Okay. But, the point is that because we always know that 0 belongs to the Clark differential there, anytime I've got one of these, guys out here, what's the point? So these guys come in sort of a one-parameter family. Associated to any outward direction, there's some little one-parameter family of tangent planes to the graph that are tangent to the graph. Hence, I can reduce by one dimension. Okay? So that's the idea. Okay, good. All right. So, how does this help? So I claim we can use this to establish the hypotheses of corollary A for the current n of f and the set A. Okay? Okay, so here's the claim. N of f. So what about N of f? So N of f is Legendrian, formally. It's compactly supported. What else? It has boundary 0. I just need to show that it satisfies the last axiom with regard to A. So in other words, for almost every Vt in this space here, if I look at N of f and I slice it by the projection to the sphere, okay, let me slice it in the negative direction. Basically, I look at all the points where so if V is up, I always look at all the points where the normal is down, okay, and I restrict it to, say, HVT. So HVT is the space where all is this half space here. Okay, so this is some sum of delta functions. I add up all the multiplicities. I should get the other characteristic of this guy. Okay, that's the claim. That's the claim. So how can we do it? So for each of these HVTs, let me define little HVT. So HVT, of course, is a nice DC set. Maybe it's not compact, but okay, maybe it's a lot better than DC. Let me build a nice DC aura for it. So HVT of X is going to be what? It'll be, say, X dot V minus T max 0. Okay? Okay, so what is this function? So here's HVT. It's 0 here, and it grows linearly at rate 1 as I move away from as I move into the complement of the half space, and into the complementary half space. Okay? So it's an aura for the half space. Okay, so then the claim is, so subclaim for almost every Vt, if I look at my original aura, and I add to that this aura, well, these are both non-negative functions. The 0 set is precisely this guy. I claim that this guy is an aura for A intersect HVT. Okay?
Why for almost everything?
Because that's what's true. I mean, so let me explain. So maybe that's something like that. Yeah. So I mean, so what's the problem? I mean, yes, indeed, the 0 set of this function is this set, but recall what's needed to be an aura. 0 must be a weakly regular value. So in other words, I've got here I've got so let's see what's the picture. So I've got my set. Oops, that's a bad choice. Here's HVT down here. Here's A up here. Okay, so I'm just going to have to wave my hands through this thing. So I've got this aura for A, just all these little. So I'm just look at its differential cycle like that. Okay, and well, I've got all these white vectors, very well behaved differentials for the aura of the half space. And I guess what I need is that somehow when I take the Clark differential of the sum, well, what could go wrong? What could go wrong is that some of these white vectors and the red vectors might be antipodal or almost antipodal. So they might start to cancel each other and make small, so violate the weak regularity condition. Okay, but basically what this says is that doesn't happen almost all the time. Basically, the point is that, well, so if I choose one of these planes here, which is not a tangent plane to A, okay, then by construction, well, I mean, just trace it through. Homework for you. So there we go. Just trace it through from the definition. Well, it is. There's no cancellation possible. That's precisely the condition. That's no cancellation possible. So no cancellation. Bingo. Victory. Okay. Well, not quite. There's one more point. So this is okay. This subclaim is okay. But there's one more thing we need to do, which may be a slight refinement of what we said a moment ago. So now I'm trying to look at this slice for this particular associated with this half space. So I'm looking at these normal vectors like that. Okay. So additionally, not only is this
Can you take it where you have finitely many?
generically we have finitely many, right? So I've got some nice inward current. Yeah. So yeah. Yeah. Okay. So so another thing we can say is that if I look at this guy, so I claim n of f. Let me just give this a name. Let me call it omega. So I claim that if I do this corresponding slice for this aura, I claim that so here I've not restricted it. It's the whole thing is omega. So in other words, what's the point? The outward vector, the downward vectors of this intersection here certainly include these guys, but I don't get any new ones. The only new ones that might occur will be on the boundary, and again, because, well, let me not get into it, because these things are, basically never antipodal. Like these things cannot yank these guys down to minus v. Okay. And so now we can apply 1a. Now we can apply 1a. What is, if I sum the multiplicities of this guy, well, that's some number. Well, it's the Euler characteristic. That's part 1a. Basically, that's just a different version of the Gauss-Bonnet theorem. So this is the Euler characteristic of a, here's say HVT. Now we're really in. Okay, and that's that. Okay, so this argument basically is due to Pokorny Ratai. Okay, very good. So any questions? Because I think we are slightly ahead of schedule.
I feel like we have an F at hand and an A on the other hand, and why didn't we compare them?
I'm sorry?
Why did we go through the numbers?
Which numbers? These numbers here?
Yes.
Okay, so recall that the principal axiom of corollary A. So corollary A, as you may recall, gives us a set of axioms that uniquely determines a normal cycle.
And we don't have a number definition there.
That's right. That's right. Okay. So that's where we are. All right. Okay, so now we are about to head into the home stretch. So so in some way, this is sort of a model for what's going to happen next, but sort of a simplified model. But in order to do this, we first of all need to understand, well, in some sense, understand how classical kinematic formulas can be proved. So even in the smooth setting. So there's a nice way of viewing it. It's anyway. It's not. The old masters didn't write it this way, but it's sort of implicit in what they did, involving some sort of bundle theoretic constructions, and that's what we're going to do next. And then we'll see briefly. Then we'll see at the end how to connect the formal argument with the actual constructions, as I said. Okay. So at this point, let's step back from all these singular spaces, all these singular functions, and just go to the smooth category. So, or even like smooth convex sets. Let's just think about that. So I've got, say, a couple of, say, guys here, smooth, compact, convex. Just keep things easy. All right. So here's A. Here's B. Okay. And what we're going to do is move B into all possible positions. Okay, by origin-motion. SON bar being the Euclidean group, the oriented Euclidean group. So there's gamma B. And we're going to look at the intersection here. There's A intersect gamma B. Okay, and so the principal kinematic formula, the main one, talks about this guy here. So I've replaced G by gamma. I don't know why. Okay. All right, so here's one thing I want to do. So, okay, so maybe the first remark is that, actually maybe I tried to leave the singularities behind, but they keep following me. I guess I've got these singularities here and here. Okay, so even if I've got two smooth domains intersecting, singularities will occur. Okay, maybe they're not that bad, but here we are. Okay, but in any case, this thing's nice and convex. So one way of doing this or one way of expressing this is to look at, well, the normal cycle of this intersection. Integrate kappa 0, maybe I'm off by a constant, like the volume of the sphere or something, and then do that. Okay? Just haven't done much. Just Gauss-Bonnet and via the normal cycle. Okay, but here's the deal. So what is the normal cycle of this guy? Well, it sort of comes in three pieces. A red piece, a blue piece, and a green piece. Okay? So here's a green piece. It's just the part of the normal cycle of gamma B that sits inside A. And then there's a blue piece, the part of the normal cycle of A that sits inside gamma B. And then there's a little bit that sort of comes from, it's sort of the interesting part. It comes when the two things interact. Okay? Like so. So what are these things? So I guess what we get are basically I've got a normal here to A, okay, and a normal here to gamma B, and somehow I just sort of spherically interpolate between the two. Okay? So so maybe I'll write here. So here's I'll call this xi, this little vector xi. This one is gamma eta. Okay, and these guys are maybe zetas here, and they belong to this little arc between xi and gamma eta. Okay. All right, so how can we, how is this going to help us? So the idea is somehow this is the idea behind all integral geometry. Sometimes the sort of one glib description of the subject of integral geometry or of kinematic formulas or of this other style of integral geometry, which is essentially a different subject involving the Radon transform. But what these things have in common are these so-called, basically you can view all these things in terms of double fibrations, so to speak, of something. Okay. So what's the deal? So basically what I want to do is, well, yes, I'm thinking about all the possible positions of B with respect to A, just the set of all these guys here. But I want to think about that. I want to look at the whole movie at the same time. I want to look at the whole collection at the same time. So I want to look at, and so how can we do that? So I claim that this if we just sort of change our perspective a little bit, let's fix xi and let's fix eta. And let's just see, well, and let's let gamma vary, and let's just look for all the zetas that can occur. Okay? So here's what I'm going to do. I'm going to look at SRN cross SRN. Okay, I've got a xi here and an eta here. These are normals to A and B, respectively. Okay, and I've got my group over here somewhere. And strictly speaking, I'm going to have another factor of this here. Okay. And I'm accustomed to writing my double vibration this way. I'm going to put something here. Maps here and here. And this thing is going to capture all these zetas. Okay, so what is it? So I'm going to look at the set of all. How many things? I've got x's. I'm going to put zeta in the middle just because, well, zeta is in the middle. And etas and gammas. Okay, so I've got 3 elements of the sphere bundle. Okay, 1 element of the group, but I'm just going to look at the guys where a couple things work. Say first of all, where gamma of the projection of eta is the projection of xi. Okay, so the base points here match up. I can start to do this operation in the fibers. Okay, and then, well, I'm also going to say that zeta lies in that little arc between gamma eta and xi. Okay. So what is this? So now I claim that if I restrict this, so this is some kind of weird bundle, and we'll talk about that in a minute. Okay. So it's some bundle over this space. And we'll talk about the fibers, as I say. If I restrict that bundle to, say, n of A cross n of B, what am I getting? I'm getting some big picture of all these zetas labeled by where they occur in gamma. Okay? And now I can look at this. So what's going to happen? So what I'm going to do is I'm going to take this mapping here. This is going to take this point here to gamma zeta. Okay? And then what I'm going to do is if I push this into here, and if I single out one particular gamma, say gamma naught, then I get this particular picture. Okay, or at least this part of it. Okay, except of course I've omitted these parts, but they're the boring parts anyway. I'm not going to worry about those too much. All right. Okay, so this is the picture. So let's just think about what this bundle looks like. So what's the fiber? So the fiber is this. So if I take a representative point xi and eta, we might even take them to, everything's nice and homogeneous. Let's take them to be coincident. I like to call that point O bar. I don't know why. O is like the origin. O bar is like the lift of the origin.
Looking at the fiber with respect to which space?
This space. Yeah. Sorry. Yeah. Maybe I'll just. I'm short. That's my problem. It's like, yeah. So whatever. Okay, so what is the fiber? So the fiber. So if I look at some representative fiber, I take xi and eta, say, to be coincident, say both sit at the origin. So now I just basically look at those gammas that don't move the base point. Okay, so they're still sitting at the same spot. That's the stabilizer of the origin. And then what have I got? Well, so now here O bar is. Well, let's call it En. So En is just like the north pole of the nth natural basis, canonical base vector. Okay, so they're my gammas. Basically, that fulfills that. But for each, if I choose gamma, what do? I'm going to cross it with what? Say zetas, where zeta lies. Sorry, I beg your pardon. It's not a cross product. So it's a gamma zeta in SON cross, let's say the fiber at 0 of Rn. That's a copy of the sphere. Okay. Let me just satisfying a certain condition. Well, zeta lies in the arc between En and gamma En. That's it. Okay, so this is sort of this universal contraption here. So I've just got I look at all basically I'm assuming that the base points of these vectors are the same, and then I'm just going to say I hold one fixed, I move one around, and then in any possible position, I interpolate spherically along there. Okay? Now, that's usually possible, except with one exception, when these guys are antipodal. So I've got a little problem there. So maybe we'll worry about that later. But maybe that's somehow, if you look at the boundary of this thing, then this is some manifold with corners, as it turns out. It's even like got some semi-algebraic structure or something. It's like in some way as nice as can be. Okay. So I'm going to call this guy C. Okay. So this is some fiber bundle with these singular fibers, but they're nice singular fibers, equal to C. Okay. And so what do I do? So as before, so what I'm going to do is the following thing. Oh yeah, so I should say one more thing. This bundle again is also like super nice. It's got these, it's like these SON bar cross SON bar actions on everything. Everything commutes with everything else. It's like great. Okay, so that's really good. So here's what I can do. Let me take a Haar measure on the group, like a form representing the Haar measure of the group, and let me take, say, my favorite differential form kappa 0 here, the one that gives me the Gauss-Bonnet theorem. Okay. So what I'm going to do, I'm going to take this guy. I'm going to call this map, the map to SON bar. I'm going to call big gamma, and the map to SRN I'm going to call big zeta. So that's the pairs gamma zeta. Okay. So I'm going to take gamma zeta pullback of this guy. Okay. All right, and so now here's what I'm going to do. I'm going to integrate over, well, let me call this bundle is E. So let me take n of A cross n of B, the whole part of the bundle that sits over n of A cross n of B. Okay, it's like the fiber product with this fiber. Okay? Okay, so I claim that this guy here, well, okay, so the magic of slicing. So this is some current, if you will. So I can also write this as the integral over SON bar of, don't say anything yet. So I'm going to take gamma. I'm going to take this guy. I'm going to slice it by gamma. Okay. Alrighty. Now I'm going to push that down into the sphere bundle. I'm going to evaluate on kappa 0. I'm going to integrate the whole thing over the group. Okay? So this is just some combination of changing push forward, pull back, slicing, whatever. Okay. This is true. I may off by a sign. I'm always off by a sign. Okay? But the claim is that this guy here is generically equal to precisely this part of the normal cycle of the intersection. Okay? What's more, I need to massage this, process this expression a little bit more. Okay? So you recall what I'm after. I'm trying to express this thing. I'm trying to write down the kinematic formula. So the right-hand side. So here I've got here I've got like a big chunk of the integrand of the kinematic formula. Okay, so there's stuff that's missing. As I say, that's boring. It's not a problem. We'll deal with that in a minute. But this part is more interesting. So how else can we do it? So as I say, I want to express this in terms of these integrals over n of a and n of b separately. Okay, so I can also write this in the following way as the integral over n of a cross n of b. Let's see here. Yeah, okay, so this is, so let me say, let me make that point. So this is the interesting part of n of a intersect gamma b. So that's on the one hand. I guess on the other hand, I'd like to compare this, go back to that master expression, so to speak. I want to look at it differently. So basically, yeah, so maybe in some sense, again, these two expressions, this expression is what is happening here. This expression is in some sense happening here. I want to give an expression here. Okay? So what do I do? So I'm looking at that guy there. So I look at gamma zeta pullback d gamma wedge kappa 0. Okay? And now what I do is I take a fiber integral of that baby. Okay? So this, again, this thing here is like essentially a product, and basically I just sort of squeeze out all the fiber stuff. Okay? All right, so what's the deal? As I said before, let's just look at this guy here. Well, d gamma is like this invariant volume form. Kappa 0 is also invariant under the SON bar action. This guy here is like, as I say, as invariant as can be. So the claim is that this guy here, it's some element of omega star of SRN cross SRN. Okay, it's just a form here. Okay, but because everything is so invariant, it's actually SON bar cross SON bar invariant. It has to be. It's like there's no other choice. I mean, it looks really complicated, but at the end of the day, it's like nothing bad can happen. That's the whole reason for all this stuff. Okay. All right. So now we're in business. So in fact, I can now write that. I mean, it's sort of a triviality to say that this is omega star of SRN. If you'll forgive me. So basically, everything in here can be written as a product, as a sum of products, of wedge products of invariant forms from the individual factors. Okay? Of different degree. Okay, but I'm integrating over this guy, which is each of these guys has dimension n minus 1. So I only care about the ones of degree n minus 1 in each factor when all is said and done. Okay, but it turns out I know what this is. Omega n minus 1 of SRN, the invariant ones. Well, it turns out they're spanned by these guys that I talked about way back when. Well, strictly speaking, plus actually possibly other stuff that's multiples of alpha, maybe some d alpha, stuff that gets killed when we integrate it on normal cycles. So we don't worry about it. Okay, so what's the point? I'm done, at least for this part of the kinematic formula. When I actually integrate these expressions, I just get these sums of wedge products of the kappa i's on the two factors. Those give me my mu's. Okay? Well, okay, so maybe there's something left. Maybe there's this stuff here. Okay, but as I say, that's the dull stuff. That's the boring stuff. It's easy to see actually that really what you get there is just sort of the end terms of the kinematic formula. Basically, you get the integral over A of kappa 0 times the volume of B. Basically just I've just got these points. How often will this vector actually sit inside gamma B? Well, it'll be equal to the volume of the gamma B. Likewise here, I'll get these guys, these integrals times the volume of A. That's just boring stuff, the end terms of the kinematic formula. And we're done. Okay? So that's the picture. All right. So so what's left? What do we do? So that's, I mean, anyway,
Okay, good question.
I'm sorry, yeah.
So here you had a cross product with C.
Yes.
It was collapsing according to epsilon.
Yes, script E. It's not,
E.
okay.
And so my question is, can you explain again how you preserve that in collapse?
So I passed from there, so I've got these three different expressions for the same integral. Is that what you're thinking about? So
My question is how the last equality. How
this one to there.
right.
So I've got this equals that. Okay?
So
Yeah, so actually what I really, the way my typography is off. What I really should have written is that equals that, and that equals that. So this is somehow the middle term. Okay? So basically I claim that if I compare this one to that one, it's sort of, well, it's actually sort of the definition of the of the fiber integral in a sense, right? Yeah. Okay. All right. So as I say, this picture is not, it's not actually, you know, sort of written down in Santalot's book or anything like that. But it's just like, I feel it's sort of like the right way to think about it. I mean, I agree. It's sort of, it's a little bit, it's sort of, it has this sort of, maybe I don't know whether it's a bug or a feature, but it has sort of this air of sophistication, right? So, you know, but which might be a little bit off-putting for some, but it's just. I mean, it's what these bundles were made for. You know, bundles are made for this kind of construction. It works. So, you know, as I say, I kind of think of it as kind of a distillation of the classical approach. If you look at Santalot's book, essentially what he's got to be doing is this. You look at Chern's paper, well, you know, why didn't Chern introduce the bundles? I'm not quite sure, because Chern was all about the bundles, but anyway, there it is. Even Federer's paper, somehow hidden in there, is like some bundles in section 5 of curvature measures, you know. So there we are. And okay, so what's our challenge? So our challenge is to say, well, let's replace A and B by WDC sets, okay? And now we've got to do all this stuff, you know, somehow this procedure here, you know, I want to make it, you know, so what is the normal cycle? Well, it's like the boundary of this, oh crap. So, you know, and, you know, so we've got to make that work. So in order to do that, somehow there's this other key construction, which is kind of nice, which is written up there. Okay, so it's going to help things. It'll sort of smooth things out a little bit. It's sort of a natural way, in some way, of combining like both these interesting terms, the red terms, and the boring terms, the blue and green terms. Okay. So I define this vectorized version of the normal cycle, n vec of A. Okay, so basically it's an incarnation, if you will, of the normal cycle. You know, so this map little z is like the zero section. So I take the set A itself, think of it as a current, and I inject it into the cotangent bundle just by putting it at 0. Okay, and then I add to that. Then I'm going to take the normal cycle, and I'm going to just basically cone over it. Right. So there's my map. Basically, just cones the vertical part, multiplies the second factor by a constant t, and just sort of push everything out. So now, whereas before I had like vector elements of the normal cycle, now I've got these rays inside the normal cycle with endpoints at the 0 section. Their endpoints sit right at the boundary, and the nice thing is this is a nice cycle, so they sit right at the boundary of A. So if I look at all these rays together, when I look at the boundary of them, they actually cancel the boundary of the first term. This is a nice cycle. Another way of viewing it is as follows. It's kind of nice. Yes. So my favorite picture. So here we are. So there's A. So I guess here's n of A. And now what's n vec of A?
So the plane is a cotangent, the blackboard is cotangent of R.
Correct. That's right. And now, so n vec of A is this current. right? So another way of doing that, basically, so is as follows. Remember, we also had this picture. So if I looked at the differential cycle of an aura for A, looks like this. Okay. Another thing I can do is just take this thing and just start expanding. Okay, just blow everything out this way. So this stuff is all going to go to infinity and disappear, and these guys just become those vertical lines. Okay, so just another way of expressing this guy. All right, so now this NVEC basically has stuff coming from the interior that's going to help us deal with the green and blue parts. It's also got N of A itself that'll help us deal with the red parts. Everything will be fine. Okay, and yeah, good. So the hardcore math is over for me for today. But I guess I'm learning that lecture minutes are extremely precious. So I'm going to maybe here's what we do in the USA. We're just going to have a little talk, So so what do we really? So I want to finish this picture, but then I guess what I'd also like to do is talk about sort of this more general way of thinking about kinematic formulas. It's like, so kinematic formulas, I guess, in some sense, they're these very rigid things, right? So maybe they're associated with these Riemannian isotropic spaces, and the list, the list of Riemannian isotropic spaces is kind of short, actually. Like this, basically, there's a few infinite families, and then there's a few sporadic other examples, but it's just like nothing. It's like it's all in front of us. However,
You mean homogeneous spaces?
there's special kinds of homogeneous spaces. So recall what I said. So the kinematic formulas actually exist whenever in any of what I call a Riemannian isotropic space. Let me remind you what that is. It's a Riemannian manifold equipped with a group of isometries that acts transitively on the sphere bundle of the manifold. Okay, and I guess the point is that here I did the case for Euclidean space and the Euclidean group. The same picture, sort of modified suitably, applies in any Riemannian isotropic space. So this always works. Okay. So actually, it's like a few years ago, basically, this huge revolution occurred in integral geometry, and it was due to these spectacular insights of Semyon Lasker, and who started to study the notion of what he called initially convex valuations. So what are convex valuations? So classically, a convex valuation is a functional defined on, say, compact convex sets that is finitely additive. That is, if I've got A and B, then I apply my functional to the union of the two. I get the same result as applying it to the individuals minus the result applied to the intersection. So volume, of course, is such a thing. Curiously enough, Euler characteristic is another such thing. Okay? And so it turns out, actually, that if you put a few additional hypotheses on these valuations have a multiplicative structure. You can clearly add them, but it turns out there's some fancy way of multiplying these things. Okay? But so it turns out that this Lasker multiplication is intimately related to kinematic formulas. So somehow, in some sense, the kinematic formulas are artifacts of the Lasker product. So if I look at these, so these mu i's, the integrals of the kappa i's, these are valuations. These are so-called, they have different names. I'll call them classical Hadwiger valuations. Okay, they're valuations, and the kinematic formulas for these guys. Well, if I look at the multiplication table for them, well, there's actually a certain duality also on the space evaluations. The kinematic formulas are somehow adjoint to the multiplication, to a Lesker multiplication restricted to these guys, which I won't talk about in detail, but that's the case. So this leads to a whole study, a whole algebraic study of kinematic formulas. If you want to determine what these things are in general Riemannian isotropic spaces, as we've done in a few special cases, the key somehow, it's more naturally somehow for the human mind to think about these products rather than, well, these co-products are what these kinematic formulas are. Okay, some others arrows go the wrong way. Okay, but still more generally, I guess, it turns out that sort of the prototype of evaluation, in a Lesker sense, is of the following type. You've got your manifold. Maybe it's not homogeneous in any sense. And you've got some object in that space, in that manifold, like a WDC set, for example. And now I look at some family of diffeomorphisms of the manifold. Maybe it's a very rich family. So some kind of generalization of an isotropic action of a group on a Riemannian isotropic space. And what I do is, from this family, I'm going to put a measure on that family. From this measured family of diffeomorphisms, together with this object in the space, I'm going to produce a valuation. And the valuation is, to apply it to this other object, I take this test object, and I move it by one of my diffeomorphisms. I intersect the two. I compute the Euler characteristic. I integrate with respect to the given measure. That, as I say, is somehow a prototype. And in fact, I don't know, in some sense I don't understand, maybe sort of dense, or maybe even, I don't know, let's say dense, among all smooth valuations in the sense of a Lesker. What is the Lesker product? Well, suppose I have two of these families, measured families of, two objects, two measured families of diffeomorphisms. What's the Lesker product? Well, I put this in all possible positions. So I want to apply the Lesker product to a third object. So I've got x, y, and z. Moving x around this way, y around this way. I want to take this valuation I got from moving x around. I've got a valuation I got from moving y around. I want to take their product, apply it to z. So here's what I do. I take x, I put it all in all possible positions. I take y and put it in all possible positions. I intersect the two. I intersect that intersection with z. Now I take the integral, the double integral over these two measured families.
And you take Euler characteristic.
Euler characteristic, that's correct. That's the Lesker product. So in some sense, these kinematic formulas, are just, like, again, they're prototypes for a Lesker product. And a lot of us, I guess, are very excited about this whole thing. Somehow Lesker himself, I think, believes this. These valuations are, in some sense, a generalization of the idea of a smooth measure. They sort of generalize the idea of a smooth function. They say there's nothing new under the sun, but in some sense, this is a brand new tool in the theory of smooth manifolds. And probably those of us who are working on it, we're not the best mathematicians in the world, I'm afraid, but we're doing our best, and hopefully we can pass it on to those guys pretty soon. Okay, thank you.